On the 15th of August, 1918, the ground under the Celebes Sea let go with a magnitude 8.3. It remains the strongest earthquake ever recorded in the Philippines. In the town of Glan, on the shore of Sarangani Bay in southern Mindanao, the shaking lasted more than 3 minutes and destroyed every house along the coast. Then the water came. The tsunami reached about 5.5 meters at the police station, 18 feet, and up to 7 meters in places. It took the boats, the livestock, the stored food, and the standing harvest. 46 people in Glan died. Last Wednesday, the 5th of August, 2026, at 14 minutes past 12 in the afternoon, an earthquake struck offshore of southern Mindanao. And the town that recorded the strongest shaking was Glan. Same coastline, same trench, 108 years apart. Now, I want to be careful here, because that is a striking pairing, and striking pairings are exactly where this sort of channel usually goes wrong. Wednesday's earthquake was a magnitude 6.4. Nobody was hurt, no damage was expected, and none has been reported. On its own, it is an unremarkable event on one of the most seismically active plate boundaries on Earth. But seismologists across the region did drop what they were doing when it came in, and they did it for a specific reason that has nothing to do with the size of it. There is a question they needed answered, and it was not how big was it, it was where exactly. That question has now been answered, and the answer is the reason for this video. I am going to build to it properly because it only makes sense once you understand what actually broke, how deep, and how we know. No guessing, no dramatizing, just the numbers, the mechanism, and the stakes. Before we start, if you felt this one in General Santos, Glan, Kiamba, Malapatan, anywhere across Sox Sargent or Davao Occidental, tell me in the comments where you were. And if you are still dealing with damage from June, say so, because I suspect a lot of people watching are. Subscribe if you want the plain version of these, and a thumbs up helps. Let us go for 5,000. Now, let us get into it. Start with the confusion, because it was real and it needs clearing up. The first bulletin out of PHIVOLCS, the Philippine Institute of Volcanology and Seismology, put this earthquake at magnitude 7.0, with an epicenter more than 200 kilometers out from Mindanao. The second bulletin put it at magnitude 6.4, 37 kilometers southwest of Balut Island in the municipality of Sarangani, Davao Occidental, at a depth of 13 kilometers. The magnitude dropped by 6/10. The epicenter moved by a very long way. The USGS, working independently, landed at 6.3 and put it under the Celebes Sea, about 104 kilometers south of General Santos City. PHIVOLCS director Teresito Bacolcol explained it directly to reporters. Initially, it was a magnitude 7.0, he said, but based on their calculations, it was 6.4. And on the location, earlier it was more than 200 kilometers away, and now, based on recalculations, it is around 50 kilometers from the epicenter of the 7.8 event. Predictably, some people online read that revision as a cover-up. Agencies caught quietly walking back the real number. So let me explain what actually happens, because the real reason is more interesting than the conspiracy. The first bulletin is automatic. A computer takes the earliest wave arrivals from whichever seismic stations report fastest and solves for a location and a size, with no human involved. Speed is the entire point. You want something out in under a minute. Now think about the geometry here. This earthquake was offshore in the Celebes Sea. Seismic stations sit on land, which means every station that recorded it early was on one side of it, with open ocean on the other. Seismologists call that an azimuthal gap, the angular slice of directions from which you have no observations. When the gap is large, the solution is well constrained across the array and badly constrained along the axis pointing out to sea. The algorithm can slide the epicenter a long way in that direction and still fit the data almost as well. That is a known, documented failure mode. It is precisely why that first bulletin was labeled automatic. The revised solution used more stations, a longer time window, human analysts, and a different method for magnitude, one that does not saturate the way quick amplitude measurements do on larger events. The revision trail is not concealment. It is the working being shown. Now the intensities, because there is a lesson in them. PHIVOLCS logged intensity 5, strong shaking in Glan, intensity 4 in Kiamba, General Santos City, Malungon and Alabel, and in Tupi and Palomaloc in South Cotabato. Intensity 3 in Masim, Maitum, and Malapatan, and out to Lake Cebu, Tampacan, and Digos City. Intensity 2 as far as Coronadal, Surala, Kidapawan, and towns in Sultan Kudarat. Notice that Glan, which is not the closest town to the epicenter, recorded the strongest shaking. That is not an error, and it points at something worth understanding. Magnitude and intensity are different quantities. Magnitude is one number for the whole earthquake calculated from the energy radiated at the source. Intensity is local, a separate value for every place, describing what the ground actually did there. Intensity depends on distance, on the direction the rupture propagated, and above all, on what you are standing on. Loose sediment, reclaimed land, and river deposits amplify shaking substantially. Bedrock does not. Two towns equidistant from the same epicenter can report completely different intensities, and both readings can be correct. Glan sits on the shore of Sarangani Bay, on sediment. Right. Now, what actually broke? When seismologists want to know the mechanism of an earthquake, not just where and how big, but what geometry of rock moved which way, they compute something called a moment tensor. It is a mathematical description of the forces at the source, worked out from the pattern of seismic waves radiating in every direction. Different mechanisms produce distinctly different patterns, and the pattern is recorded by stations all over the world. One number that falls out of that calculation is the double couple percentage, how closely the recorded waveforms match what you would expect from one block of rock sliding past another along a single flat surface. For this earthquake, the reported solution came back around 92% double couple. That is high, and it rules things out. An explosion produces a large volume change signature. A fluid-driven or volcanic source produces a distinctive component of its own. Neither is present here. This was rock sliding against rock. The geometry backs it up, a shallow event, both candidate fault planes striking northwest to southeast, parallel to the trench, with the maximum compression pointing roughly west-southwest to east-northeast. That direction is not arbitrary. It is almost exactly the convergence direction where the floor of the Celebes Sea is being pushed eastward beneath Mindanao, which is the Cotabato Trench. And Bacolcol said so plainly, the magnitude 6.4 earthquake was caused by the Cotabato Trench. He also classified it as an aftershock of the magnitude 7.8 of the 8th of June, and gave a nice piece of seismology while doing it. By definition, he said, the maximum aftershock is about 1 magnitude unit below the main shock. So for a 7.8, the largest aftershock you would expect is around 6.8. That rule of thumb has a name, Both's Law. Empirically, across sequences worldwide, the largest aftershock tends to come in around 1.1 to 1.2 magnitude units below the main shock. A 6.4 sits comfortably inside that. But here is where it gets interesting, and this is the part that made people look twice. The June main shock, the magnitude 7.8 that killed more than 100 people, was located at a depth of roughly 33 kilometers by PHIVOLCS, and deeper still by the USGS. Wednesday's earthquake was at 13 kilometers. Some solutions put it shallower still. That is a large difference, and it means this rupture did not happen on the patch that failed in June. It happened well up dip, further along the subduction interface toward the trench itself, closer to the seafloor, above the depth range where the June rupture lived. So the word aftershock is accurate in the statistical sense and slightly misleading in the physical one. This was not the same fault surface failing again. It was a different part of the same system loaded by the first one. There are two structures that fit. One is the shallow, near-trench section of the megathrust itself, the part of the plate interface closest to the trench axis. The other is a splay fault in the accretionary wedge. The accretionary wedge is worth a minute, because most people have never heard of it, and it does a disproportionate share of the damage in subduction earthquakes. When one plate descends beneath another, the sediment sitting on top of the descending slab does not all go down with it. Much of it gets scraped off, the way a bulldozer blade peels material off a road, and piles up against the leading edge of the overriding plate. That pile is the accretionary wedge. It is young, weak, waterlogged, and cut through with faults that branch upward off the main plate interface and angle toward the seafloor. Those branches are splay faults, and they matter for one specific reason. When a splay fault slips, it moves shallow rock very close to the seafloor, which is exactly the geometry that lifts water. Which brings me to why a tsunami bulletin was issued at all. 12 minutes after the shaking, NOAA issued a tsunami message from Mindanao. It carried no warning status and reported no impact. The USGS tsunami flag read 0. Coverage on the day correctly said no tsunami warning was triggered. The more precise description is that the system evaluated the event and issued a no-threat product. It fired, ran the numbers, and stood down. That is the system working. But it is worth understanding why it bothered, and the reason is one of the more uncomfortable facts in subduction zone science. Shallow thrust earthquakes near a trench can generate tsunamis out of all proportion to their magnitude. The rock up there is weak and low in rigidity, which means the same amount of energy produces more slip. They often rupture slowly, which radiates less high-frequency seismic energy, so they feel smaller than they are. And because they are shallow and near the seafloor, more of that slip goes into vertical displacement of the water column. There is a name for the extreme version, a tsunami earthquake, an event that produces a wave far larger than its magnitude suggests, and that people on shore may barely feel before it arrives. At magnitude 6.4, that was not a practical concern on Wednesday, and nothing happened. But the very first bulletin said 7.0 at this depth with this geometry, which is exactly why the system ran a full evaluation rather than dismissing it. For scale, the June 7.8 produced confirmed waves of roughly 1 to 1.5 meters across coastal areas of Sultan Kudarat and Sarangani. A meter of water does not sound like much. It is enough to take you off your feet, carry you into debris, and pin you there. Now the history, and this is what the seismologists were actually checking. The Cotabato Trench has produced two great earthquakes in the instrumental record. The first is 1918, the magnitude 8.3 I opened with, the strongest in Philippine history, which destroyed Glan. The second is 1976, the Moro Gulf earthquake, magnitude 8.1. Its rupture zone sits north of the 1918 rupture toward the Moro Gulf. The tsunami it generated killed thousands. Two magnitude 8 class events, 6 decades apart, on adjacent sections of the same trench, which tells you the Cotabato Trench is capable of producing multiple great earthquakes, and researchers at PHIVOLCS have been paying close attention to it for months. Since January, there has been a swarm of moderate earthquakes along the trench, sitting inside the 1976 rupture zone, which they have named the Calamansig Swarm. So the question that mattered on Wednesday was not the magnitude. It was whether this rupture had happened on the stretch of trench that has been quiet, the section between the historical ruptures, the part carrying the longest accumulation of unreleased strain. And the answer is no. Wednesday's earthquake happened at the southern end of the June aftershock zone. The quiet stretch is to the north. It did not move. Before the answer, one thing to clear up. You will see claims that the magnitude was suppressed or that something artificial triggered this. The revision is explained by station geometry, and the mechanism is 92% double couple with a compression axis pointing exactly where plate convergence predicts. There is nothing in that data consistent with an explosion or an injection, and there is no plausible mechanism by which anything human moves a subduction interface. So, does Wednesday's earthquake mean the pressure has been released? No. And the arithmetic on that is brutal. Magnitude is logarithmic. Each whole step up is roughly 32 times the energy. From 6.4 to 7.8 is 1.4 steps, which works out to something on the order of 150 times more energy in the June event than in Wednesday's. Put that against the loading. This plate boundary has been converging continuously since before 1918. On a locked fault segment, a century of convergence accumulates a slip deficit measured in meters. A magnitude 6.4 consumes essentially none of it. Nothing meaningful was drained on Wednesday. If anything, the physical significance runs the other way. A nearby structure failing up dip is the signature of stress being transferred onto neighboring rock by the June rupture, which is the mechanism by which large earthquakes propagate along a plate boundary over months and years, not the signature of a sequence winding down. But here is the actual answer to the question in the title. What are scientists on alert about, and what are they watching? Not magnitude, direction. This is the part I find genuinely elegant, and it requires no new science and no special access to see. If aftershock activity keeps decaying the way it is supposed to, following Omori's law, where the rate falls off roughly in inverse proportion to time since the main shock, then this sequence is doing what sequences do: ordinary, expected, fading. But if the clusters of magnitude 4 and 5 events start stepping progressively northward toward the quiet section of the Cotabato Trench, that is a completely different observation. It would mean the loading is migrating along the boundary toward the segment that has not released. You do not need a seismologist to spot that. You need the public earthquake catalog and a map, and the patience to watch where the dots land over weeks. That is what scientists are on alert actually means in practice. Not a countdown, not a prediction. Nobody can predict earthquakes. Foreshocks are only ever identifiable in hindsight, and that quiet segment could release in a decade or in a century. Anyone offering you a date is selling something. It means a specific, publicly documented piece of fault is carrying a very long accumulation of strain, and the honest position is that it is unpredictable rather than imminent, which is, in its way, more unsettling than any theory about hidden numbers. So, What do you do if you are in southern Mindanao? The most important thing is specific to right now, and it is about your walls. PHIVOLCS said no damage was expected from Wednesday's shaking, and that assessment is calibrated against structurally sound buildings. But across this corridor, June already cracked an enormous amount of masonry, over 120,000 homes damaged or destroyed. A magnitude 6.4 shaking an intact wall, and a magnitude 6.4 shaking a wall that has been barely holding since June are not the same event. If your house was damaged in June and has been shaken again, get it looked at before you sleep another night in it. If you are on the coast and the shaking is strong or long, do not wait for a warning. For a near-trench earthquake, the wave can arrive before an official bulletin does. Strong shaking, or shaking that goes on for a long time, is itself the warning. Move inland and uphill immediately. And know that a near-trench thrust can feel weaker than it is. The 1918 shaking at Glan lasted over 3 minutes, and the water followed. Learn your evacuation route now while nothing is happening. PHIVOLCS and local DRRM offices publish tsunami hazard maps for this coastline. Glan is still there. It was rebuilt after 1918, and it has been rebuilt after everything since. And on Wednesday, it recorded the strongest shaking in the country from an earthquake that harmed nobody. The trench that destroyed it is the same trench. It has been converging the entire time, through 1918, through 1976, through June, through Wednesday, and through this sentence. What changed last week is not the danger. It is that we now know slightly more precisely where the danger is not. Tell me in the comments where you were and what you felt. Subscribe if you want the follow-up, because I will be watching where those dots land. And thank you for giving me this much of your afternoon. I will see you next time.